So all protons in a molecule typically are not going to absorb the same frequency, because if they did, then every spectrum would just have one signal. And that is not very useful for us, right? In spectroscopy, we need to have different signals based on different aspects of the molecular structure for us to be able to determine what is going on in the molecular structure. So protons in the same molecule can absorb at different frequencies because of the electron cloud that surrounds the nucleus. So what you're looking at here is a nucleus, and then we have an electron cloud that's surrounding that nucleus. Like any moving charges, the electrons that make up the cloud experience a force from that external magnetic field, okay? So, and that causes the electrons to move in a circular pattern. So we have electrons there. You're going to get this external magnetic field, and it's going to make them go in a circular pattern. This is their own magnetic field is called B local, and we're going to talk about that in a second. And then when that's added to this external magnetic field, that gives us our effective magnetic field. So this equation is really helpful to understand why we get different peaks, because every nucleus is going to have its own different local magnetic field here, okay? And so that's one of the reasons why we get different peaks. So put some words to that. So like I said before, the moving electrons create their own magnetic field lines, and at the nucleus, those magnetic field lines result in a local magnetic field, okay, that is opposite the direction of the external magnetic field. So that creates a local magnetic field, and we're going to call that B local, okay? And that's in opposition to the external magnetic field. Now, the sum of the two magnetic fields is the effective magnetic field, and that's what's felt by the nucleus. All right, and that's represented with the equation there. Now, B local and B external are going to have opposite signs. So B local and the magnetic field, the external magnetic field, have opposite signs. So B effective is smaller than the external. So basically, the B effective will always be somewhat less than the external magnetic field, because we're going to subtract out that B local, right? So the protons are said to be shielded. Okay. Now, the extent of shielding for a particular nucleus, and therefore B effective, depends on the surrounding electrons and the atoms within the nucleus. So that depends on the chemical environment, right? So, for example, if you have a proton that's next to an oxygen, that's going to have a different chemical environment that, say, is one next to a carbon, okay? Now, protons that are in identical chemical environments, which are called homotopic or chemically equivalent, have the same B effective. So, protons in identical chemical environments right? And if you're identical chemical environments, they're called homotopic. Or chemically equivalent. Have the same effective magnetic field, okay? Now, on the other hand, protons that are in different chemical environments are called heterotopic. I think I said tropic before. It's homotopic and heterotopic. Or they are chemically distinct. Okay, and these guys are going to have a different effective magnetic field. Now, as we previously saw, protons that are exposed to different magnetic fields absorb photons at different frequencies. And if we put all these ideas together, we arrive at one of the most important rules for NMR spectroscopy, and that's that each chemically distinct type of hydrogen atom in a molecule gives rise to an individual signal in a proton NMR spectrum. So it's really important for us to be able to identify things that are chemically identical versus chemically different. So, for example, if we look at the proton NMR spectra of propanoic acid, okay, propanoic acid has 2 hydrogen atoms. It's got 1 hydrogen atom here and it has 1 hydrogen atom here. So how can we tell by looking at the molecular structure whether these 2 protons are in different chemical environments and are distinct? And so basically, honestly, one of the easier ways to do this is to look for symmetry. There's no symmetry in this molecule, right? There's only 1 proton attached to this carbon and only 1 proton attached to that alcohol. Those are going to be different chemical environments, okay? This is the way I learn. This is the way I do it when I personally work these problems. But your book uses a different method, and so we'll talk more about the method that I prefer versus your book in class. But you may work better with the book method, and so I don't want to discount that. So one way that Carty particularly talks about this is to look for a unique point of reference within the molecule and determine how close the protons are to that reference. So if the protons are located at different distances from that unique point of reference within a molecule, then those protons are going to be chemically distinct and definitely give rise to different proton NMR signals. So when we look at propanoic acid, there are a lot of different unique points of reference, but let's choose the terminal carbon atom of the triple bond. So we're going to look at this carbon atom of the triple bond. The proton on the left, this guy, is closer to the carbon atom than the proton on, well, I've got my left and right. The proton on the right is closer to the carbon atom than the proton on the left, okay? So that means they're distinct. That's it. So the molecule generates 2 signals in the NMR spectrum, right? We've got 1 signal here and we have 1 signal here. Again, ppm here is going to stand for parts per million. And note this third signal that's at 0 ppm, that is tetramethyl silane, okay, which is just added as a reference. People add that as a reference. It's always going to be lower than carbon. And so you set the instrument for that to be 0. And so that's how we're able to know where certain protons show up. So let's look at another example where we're trying to figure out how many we get. So when I look at this example, when I personally work this, and I'm looking at Br CH2 C 1 2 3 C H, okay, I see first off there's no symmetry, but those, and I drew that a little off, Those hydrogens right there are on the same carbon. And as long as there's no cis and trans or anything unusual, if you have hydrogens that are on the same carbon, they are going to be in the same chemical environment. Now, like I said, there are some exceptions to this. One of the most notable that you'll see is if there's some sort of cis or trans isomers. So there's some sort of distance around the double bond and something else that's very electronegative. But I would say 99% of the time, if you've got two hydrogens that are on the same carbon, they're going to be in the same chemical environment, right? Now, they're in a different chemical environment than that hydrogen over there by the triple bond. So I can automatically look at this and say, well, there's no symmetry. So we're going to get two signals here, right? And that's correct, okay? Now, the way that he talks about this is he says to choose a unique point of reference. So he chose the bromine atom when he did this as the unique point of reference. And he says, look, we can see that these protons are closer to the bromine than this guy over here, right? And therefore, these are distinct versus that one. And then he says, look, these have the same distance away from the bromine, and so these are going to be in the same chemical environment. And you can see that spelled out there. So I want to do another example here, just really, really quickly about things that are like how many distinct protons you can have. So, for example, if I have CH3, CH2, CH2, CH3, okay, and I look at this spectrum, there is a point of symmetry. The point of symmetry is right here. That means these protons and these protons are in the same chemical environment. And these protons and these protons are also in the same chemical environment. And so that means that we end up with two signals here, okay? Because they're in the same chemical environment. If we look at this molecule, there is also a point of symmetry right here. And so you have these protons, right? And so we do kind of use Carty's principles here, where I choose my plane of symmetry when there's symmetry, and I say, okay, there's those protons. And I say, look, these protons shown here in blue are the same distance away from that center carbon. And then these protons shown here in red are the same distances away as well. And so this would result in three signals. Okay, so that's what we are looking for here. Let's do an example. Consider the number of proton NMR signals that should be generated. Determine which spectra, 1 or 2, was produced from dichloroacetic acid shown here. So when we look at this, we see dichloroacetic acid, and we see there are two spectra. The spectrum 1 here has 2 peaks, and spectrum 2 here has 1 peak. And that's really the only difference between these. So what this question is really asking is, hey, look, do you expect 1 or 2 peaks from this molecule? And then to kind of dig down deeper, it's saying, look, does that mean, are these two protons chemically equivalent? That's what this is asking. Now, on the next slide, I have a table for you that gives you some questions to think about. One is there a unique point of reference in this molecule? And there are many unique points of reference. Another way to say that is there's no symmetry. And so we can use, for example, the oxygen right here. And it says, look, are the protons the same distance from that point of reference? Well, this hydrogen's much closer to the oxygen than this hydrogen is. So they are not the same distance, that means that these two are distinct. So what we have here are two distinct protons. So we have two distinct protons. And because we have two distinct protons, that's going to give us two distinct signals. And so the two distinct signals means that it's going to be associated here with the first spectra. So that's a way that we can use the number of protons to figure out and identify which spectra that is associated with that. Now, we've already a little bit about symmetry, but we're going to go ahead and talk about it again. If we look at heptane, for example, it's a symmetric molecule and it's not going to have a unique point of reference. And so we could easily choose either end. And so you can see what he has done here is the same thing that we talked about, right? Here's your point of symmetry, and then each of the molecules A, B, and C are the same distance from that point of symmetry. So for example, the C's are the same distance from D, and the B's are the same distance, and the A's are the same distance. So you're only going to get 4 signals with heptane, okay? And so let's look at another example. So this example says, look, how many distinct types of protons are there in the following molecule? And so I, of course, really love to look for symmetry. Now, when we look at this, if the symmetry is hard for you to see because of how it's written, you are always more than welcome to rewrite it. And so that's what I'm going to do right now. That's CH3, CH, boop, boop, CH, C, CH3, boop, boop, C, CH3. I got lost there for a second. CH, 1, 2, CH, CH3. Now, I always like to go back and double check myself because I do get lost sometimes. There's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Always feel free to go back and check it yourself as well. Now, as I look at this, I say, hey, there is a plane of symmetry, right? Which means it's the same on both sides. And that plane of symmetry is right through that double bond. So it's going to intersect that double bond. And so what we see here are, and remember, we're just looking for protons. We are not looking for at carbons. This is protons. So look at those protons. So we have these two CH3s that are equal distance from that point of symmetry. And then we have this CH and this CH here. And then this CH and that CH there. And then I need another color. Let's do pink. And that CH and that CH there. And so when we look at this, if we look at our different colors, we see here that we have 4 distinct signals, right? By finding that plane of symmetry. I find that that's the easiest way to do problems like this, is to look for that plane of symmetry. Now, he also talks for a while in this chapter about a chemical distinction test. And when we look at the chemical distinction test, basically what he says is, for each hydrogen atom in question, draw the complete structure of the molecule in which just that hydrogen atom is replaced by an imaginary atom X. If the X substituted molecules are either identical or enantiomers, then the corresponding hydrogen atoms in the original molecule are chemically equivalent. If the X substituted molecules are either isomers or diastereomers, then the corresponding hydrogen atoms in the original molecule are chemically distinct. Now, when we look at this, right, he's showing this molecule, HOCH2 C, and we've got Cl and Cl and H, okay? And he's saying go through and replace all of these. And so if you look, he's saying, look, if you replace the H here with an X, and then you replace that H there with an X, A and B are going to be constitutionally isomers, and therefore they're distinct. Just honestly, I feel like an easier way to do this is to look at this molecule and say, there is no point of symmetry. This hydrogen is connected to that carbon, which is in a different chemical environment than these two hydrogens here, which is in a different chemical environment than that hydrogen there. These two guys, if you were to replace them and relate them to each other, which is what he's doing in this one and in this one, then he's saying, look, they're enantiomers and these two are equivalent. I think it's just easier to say, unless you're dealing with double bonds and cis and trans, which is 99%, you're only going to see that 1% of the time, then it's just easier to say, look, those hydrogens on that carbon are going to be in the same chemical environment. And so out of this, we get 3 signals. It's just, to me, a faster way to do this. So, there we go. So, let's look at this particular question. It's saying, look, using the chemical distinction test, determine how many chemically distinct carbon atoms there are in chloroethane, which is H2C double bond CHCl, right? And so when you look at this, this is one of those exceptions, right? Double bonds are where we see those exceptions. And so because they spread out like this, right? And so when you look at this, there is a different distance between this hydrogen and that chlorine than this hydrogen and that chlorine. So then we can say, look, these two are in different chemical environments. And then, of course, this one has a different distance as well. So double bonds are really the only time you're going to experience this. And you're not going to see it with every double bond. You're really just going to see it when you're close to something that's very electronegative, like this example. And so this would be one of those exceptions where you do get 3 signals, okay? But understand, this is very rare, and in your packet, you are not going to see that at all. There's not going to be a good enough way to see the distinction there in the packets that you have. So what you can definitely depend on is that unless you've got something that's really electronegative, right, is that they're going to be in the same chemical environment. Looking for points of symmetry is going to be really, really helpful. And again, we will do more examples in class before you work on your packet. I have